Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. The study of soil composition and mineral distribution across temperate biomes represents one of the most methodical and quietly absorbing branches of earth science, a field in which researchers have spent decades cataloging the subtle variations in particle size, chemical makeup, and organic matter content that distinguish one patch of ground from another. It is a discipline defined by incremental observation, by the patient accumulation of data points gathered from countless soil pits, auger borings, and laboratory analyses, all contributing to an ever more detailed portrait of what lies beneath the surface of the world's temperate landscapes. The temperate biomes themselves, stretching across broad swaths of the northern and southern hemispheres between roughly 30 and 60 degrees of latitude, encompass an extraordinary range of environments, from deciduous forests and mixed woodlands to grasslands, shrublands, and transitional zones where one vegetation type gradually gives way to another. In each of these settings, the soil has developed over thousands or even millions of years through the slow, relentless interaction of parent rock material, climate, living organisms, topography, and time. The 5 classical soil-forming factors, first articulated by the Russian soil scientist Vasily Dokuchev in the late 19th century and later refined by the American pedologist Hans Jenny in his landmark 1941 publication. The mineral fraction of any given soil sample typically constitutes the overwhelming majority of its total mass, often accounting for somewhere between 92 and 98% of the dry weight in mineral soils, with the remainder consisting of organic matter in various stages of decomposition. This mineral component is itself composed of particles spanning a wide range of sizes, from coarse sand grains measuring between 2 millimeters and 50 micrometers in diameter, to silt particles falling between 50 and 2 micrometers, to the finest clay particles, which measure less than 2 micrometers across. The relative proportions of these 3 size classes determine what soil scientists refer to as the soil texture, a fundamental property that influences virtually every other aspect of soil behavior, including its capacity to retain water, its permeability to air and roots, its tendency to shrink and swell with changes in moisture content, and its ability to hold and exchange nutrient ions. A soil composed predominantly of sand, for instance, will drain rapidly and offer relatively little resistance to root penetration, but it will also retain fewer nutrients and less moisture than a soil rich in clay. Conversely, a heavy clay soil may hold abundant water and nutrients, but can become waterlogged and compacted, presenting its own set of challenges for plant growth and microbial activity. The chemical composition of the mineral fraction varies enormously depending on the nature of the parent material from which the soil has developed. In regions underlain by granitic or felsic igneous rocks, the dominant minerals in the soil tend to include quartz, various feldspars such as orthoclase and plagioclase, and micas including both muscovite and biotite. Quartz, composed of silicon dioxide with the chemical formula SiO2, is particularly resistant to chemical weathering and tends to accumulate in the sand and silt fractions of mature soils, forming a kind of skeletal framework around which other minerals weather and transform. The feldspars, by contrast, are considerably more susceptible to chemical breakdown, particularly in the presence of slightly acidic water. And their gradual decomposition produces a suite of secondary clay minerals along with dissolved ions of potassium, sodium, calcium, and aluminum. This process of feldspar weathering is one of the primary sources of clay minerals in temperate soils and has been studied extensively in laboratory and field settings for well over a century. In temperate regions where the bedrock consists of sedimentary materials such as limestone, sandstone, or shale, the mineral composition of the overlying soil reflects the chemistry of these parent rocks in characteristically different ways. Limestone, composed primarily of calcium carbonate with the formula CaCO3, dissolves relatively readily in acidic rainwater through a process known as carbonation, leaving behind an insoluble residue of clay minerals, iron oxides, and small quantities of other resistant minerals that gradually accumulate to form what is known as a residual soil. These limestone-derived soils, often classified as alphasols or molysols in the USDA soil taxonomy system, tend to be relatively rich in calcium and magnesium and to maintain a near neutral to slightly alkaline pH, conditions that are generally favorable for a wide range of plant species and soil organisms. Sandstone-derived soils, on the other hand, tend to be sandier in texture, more acidic, and lower in base cations, reflecting the predominance of quartz and the relative scarcity of easily weatherable minerals in the parent rock. The clay minerals that form through the weathering of primary minerals are themselves a diverse and scientifically fascinating group, classified into several major families based on their crystallographic structure and chemical composition. The most common clay mineral groups found in temperate soils include the kaolinite group, the smectite group, the alite group, and the vermiculite group, each with distinctive properties that profoundly influence soil behavior. Kaolinite, a 1:1 layer silicate with the general formula Al2C2O5OH, 4, consists of alternating sheets of silicon-oxygen tetrahedra and aluminum-oxygen hydroxyl octahedra bonded tightly together, resulting in a mineral with relatively low surface area, low cation exchange capacity, and minimal tendency to shrink and swell. It is the dominant clay mineral in many highly weathered tropical soils, but also occurs in temperate soils derived from acidic parent materials or those that have undergone extensive leaching over long periods of time. The smectite group of clay minerals, by contrast, includes minerals such as montmorillonite and baydellite that possess a 2:1 layer structure in which an octahedral sheet is sandwiched between two tetrahedral sheets. What makes the smectites particularly noteworthy from a pedological perspective is the weakness of the bonds between adjacent 2:1 layers, which allows water molecules and exchangeable cations to penetrate into the interlayer spaces, causing the mineral to expand significantly when wet and contract when dry. This shrink-swell behavior is responsible for the characteristic deep cracks that appear in smectite-rich soils during dry periods, a phenomenon that has important implications for engineering, agriculture, and ecosystem function. Soils dominated by smectite clays, often classified as vertisols when the shrink-swell properties are extreme, are found in various temperate settings, particularly in regions underlain by basic igneous rocks or marine sediments rich in magnesium and iron. Illite, another 2:1-layer silicate, differs from the smectites in having potassium ions firmly wedged between its structural layers, which prevents the interlayer expansion that characterizes the smectites. As a result, illite-rich soils tend to exhibit less dramatic shrink-swell behavior than smectite-rich soils, though they still possess moderately high cation exchange capacities and surface areas. Illite is particularly abundant in soils derived from shales, mudstones, and glacial deposits in temperate regions, and it is often the most common clay mineral in the soils of the northern United States, Central and Northern Europe, and parts of Russia and China. The formation of illite from the weathering of muscovite mica is a well-documented process that involves the gradual replacement of interlayer potassium with hydrated cations, followed by partial collapse and reorganization of the crystal structure, a transformation that can take place over timescales ranging from decades to millennia, depending on the specific environmental conditions. Vermiculite, the fourth major clay mineral group, shares the 2:1-layer structure of the smectites and illite, but has a somewhat more restricted capacity for interlayer expansion. It typically forms through the weathering of biotite mica and certain chlorite minerals, and it is particularly common in soils developed on mafic and intermediate igneous rocks, as well as some metamorphic parent materials. Vermiculite possesses a very high cation exchange capacity, often exceeding that of the smectites on a per gram basis, making it an important reservoir of plant-available nutrients in the soils where it occurs. The distribution of vermiculite in temperate soils has been mapped in considerable detail in several regions, and studies have shown that it tends to be most abundant in moderately weathered soils where the transformation of biotite is actively occurring, but has not yet progressed to the point where the vermiculite itself begins to degrade into simpler mineral phases. The organic matter component of temperate soils, though typically representing only a small fraction of the total soil mass, exerts an influence on soil properties that is far out of proportion to its abundance. Soil organic matter, often abbreviated as SOM, consists of a complex mixture of partially decomposed plant and animal residues, microbial biomass, and a more stable fraction known as humus, which is composed of large, complex organic molecules that resist further decomposition and can persist in the soil for centuries or even millennia. The amount of organic matter present in a temperate soil varies widely depending on the balance between organic inputs from vegetation and losses through decomposition, erosion, and leaching. In general, grassland soils tend to accumulate more organic matter than forest soils in comparable climatic settings, a difference attributed to the dense, fibrous root systems of grasses, which contribute large quantities of organic material directly to the soil profile and to the drier conditions that often prevail in grassland environments, which slow the rate of decomposition. The distribution of organic matter within the soil profile follows a characteristic pattern in most temperate soils, with the highest concentrations found in the uppermost horizons and a gradual decline with increasing depth. In a typical forest soil, the organic-rich surface layer, known as the O-horizon, may consist of several centimeters of recognizable leaf litter and partially decomposed plant material overlying a mineral A-horizon in which organic matter has been intimately mixed with the mineral fraction through the activities of earthworms, insects, and other soil organisms. The A-horizon of a temperate forest soil typically contains between 2 and 8% organic matter by weight, though values outside this range are not uncommon. Beneath the A-horizon, the organic matter content generally decreases to less than 1% in the B and C horizons, though roots and dissolved organic compounds may transport small amounts of organic material to considerable depths. In the grassland soils of the temperate zones, the organic matter distribution is often somewhat different, with a thick, dark A-horizon known as a molic epipedon extending to depths of 30 centimeters or more and containing organic matter concentrations that may range from 3 to more than 10%. This deep distribution of organic matter in grassland soils reflects the contribution of grass roots, which can extend to depths of 2 meters or more, and which die and decompose in place, gradually enriching the surrounding soil with organic carbon. The resulting soils, classified as mollysols in the USDA taxonomy, are among the most naturally fertile soils on Earth and have historically supported some of the world's most productive agricultural systems, including the grain belts of the American Midwest, the Ukrainian steppe, and the Argentine pampas. The interaction between organic matter and the mineral fraction of the soil gives rise to a number of important chemical and physical processes that influence soil fertility, structure, and behavior. One of the most significant of these is the formation of organomineral complexes, in which organic molecules become adsorbed onto the surfaces of clay minerals or bound to iron and aluminum oxides through a variety of chemical mechanisms, including ligand exchange, cation bridging, and van der Waals interactions. These organomineral associations are thought to be one of the primary mechanisms by which soil organic matter is stabilized against microbial decomposition, and they may account for a substantial fraction of the long-term carbon storage capacity of temperate soils. Research conducted at numerous field sites across the temperate zones has demonstrated that the stability of soil organic matter is closely correlated with the abundance and type of clay minerals present, with smectite-rich soils generally showing greater organic matter stabilization than soils dominated by kaolinite or quartz. The pH of temperate soils, a measure of the concentration of hydrogen ions in the soil solution, is another fundamental property that both reflects and influences the mineral composition and nutrient status of the soil. Most temperate soils fall within a pH range of approximately 4.5 to 8.0, with forest soils on acidic parent materials tending toward the lower end of this range and grassland soils on calcareous substrates occupying the higher end. The pH of a soil affects the solubility and availability of virtually every plant nutrient, with some elements such as iron, manganese, and zinc becoming more soluble and available under acidic conditions, while others, such as phosphorus, calcium, and magnesium, are most available in the neutral to slightly alkaline range. The pH also influences the activity and composition of the soil microbial community, with bacteria generally favoring neutral to slightly alkaline conditions and fungi being more tolerant of acidic environments. The process of soil acidification in temperate regions is driven by a number of natural and anthropogenic factors, including the leaching of base cations by percolating rainwater, the production of organic acids by plant roots and decomposing organic matter, the oxidation of reduced sulfur and nitrogen compounds, and the deposition of acidifying pollutants such as sulfur dioxide and nitrogen oxides from industrial and agricultural sources. In regions with high rainfall and freely draining soils, the progressive loss of calcium, magnesium, potassium, and sodium from the soil profile over time leads to a gradual decline in pH and a corresponding increase in the proportion of aluminum and hydrogen ions on the cation exchange complex. This process, which pedologists refer to as base cation depletion or base unsaturation, is particularly pronounced in soils developed on siliceous parent materials in humid temperate climates and is one of the principal factors driving the development of the acidic, nutrient-poor soils known as spodosols or podsols. The spodosols, found extensively in the boreal and cool temperate forests of North America, Scandinavia, and Russia, are among the most visually striking of all soil types, characterized by a distinctive sequence of horizons that record the downward translocation of organic matter, iron, and aluminum through the soil profile. Beneath the organic-rich O and horizons, a bleached, ash-gray horizon, depleted of iron, aluminum, and organic matter by the process of podsolization, overlies a dark reddish-brown to black BHS or BS horizon, in which the translocated materials have accumulated. The minerals present in the BHS horizon include various poorly crystalline iron and aluminum oxyhydroxides such as ferrihydrite and allophane, along with organometallic complexes in which organic molecules are chelated with iron and aluminum ions. The formation of these minerals and complexes is intimately linked to the chemistry of the organic acids produced by the decomposition of coniferous litter and ericaceous vegetation, which are particularly effective at dissolving and mobilizing iron and aluminum from the overlying horizons. The distribution of iron oxides and oxyhydroxides in temperate soils is a subject that has received considerable attention from soil scientists and geochemists, owing to the important roles that these minerals play in controlling the color, structure, and chemical behavior of soils. The most common iron oxide minerals found in temperate soils include goethite, an iron oxyhydroxide with the formula FeOH, and hematite, an iron oxide with the formula Fe2O3. Goethite, which imparts a yellowish-brown color to soils, is the thermodynamically stable iron oxide under the cool, moist conditions that prevail in most temperate environments and is by far the most abundant iron oxide in the soils of these regions. Hematite, which gives soils a distinctive red color, is more common in warmer and drier environments, but can also be found in some temperate soils, particularly those developed on red-colored parent materials, or those that have experienced periods of intense dehydration. The formation of goethite and other iron oxyhydroxides in temperate soils proceeds through a series of steps that begin with the release of ferrous iron from the weathering of primary iron-bearing minerals such as biotite, hornblende, augite, and olivine. The released ferrous iron is then oxidized to the ferric state in the presence of dissolved oxygen and precipitates as poorly crystalline ferrihydrite, a metastable phase with approximately the composition Fe2O3 multiplied by 1.8 H2O. Over time, the ferrihydrite gradually transforms into the more crystalline and thermodynamically stable goethite through a process of dissolution and reprecipitation, a transformation that can be influenced by a variety of factors including pH, temperature, the presence of organic matter, and the concentration of other dissolved ions. In some temperate soils, particularly those that experience periodic waterlogging and the resulting fluctuations between oxidizing and reducing conditions, the cycling of iron between its ferrous and ferric forms creates distinctive color patterns known as redoxomorphic features, which soil scientists use as diagnostic indicators of soil drainage conditions and hydric soil status. The nitrogen cycle in temperate soils is another area of pedological inquiry that has been studied with remarkable thoroughness over the past century and a half, yielding a detailed understanding of the transformations that this essential element undergoes as it moves between the atmosphere, living organisms, and the soil matrix. Nitrogen enters the soil through several pathways, including the biological fixation of atmospheric dinitrogen gas by symbiotic bacteria such as Rhizobium and Bradyrhizobium living in the root nodules of leguminous plants. The non-symbiotic fixation of nitrogen by free-living soil bacteria such as Azotobacter and Clostridium. The deposition of ammonium and nitrate ions in rainfall and dry deposition, and the addition of nitrogen-containing organic residues from plant litter, root exudates, and animal wastes. Once incorporated into the soil organic matter, nitrogen undergoes a gradual process of mineralization in which soil microorganisms break down the complex organic nitrogen compounds into simpler inorganic forms, beginning with the release of ammonium ions through a process called ammonification, and continuing with the oxidation of ammonium to nitrite, and then nitrate through the two-step process of nitrification, carried out by specialized bacteria belonging to the genera Nitrosomonas and Nitrobacter, among others. The phosphorus cycle in temperate soils presents a rather different set of dynamics compared to the nitrogen cycle, owing in large part to the relatively low solubility and mobility of most phosphorus compounds in the soil environment. Unlike nitrogen, which can enter the soil from the atmosphere through biological fixation and wet and dry deposition, phosphorus is derived almost entirely from the weathering of phosphorus-bearing minerals in the parent rock, the most important of which is apatite, a calcium phosphate mineral with the general formula Ca5, PO4, 3, FClOH. As apatite weathers under the influence of acidic soil solutions, it releases phosphate ions into the soil solution, where they can be taken up by plant roots, immobilized by soil microorganisms, or adsorbed onto the surfaces of iron and aluminum oxides, clay minerals, and calcium carbonate particles. This adsorption process, which soil chemists refer to as phosphorus fixation or phosphoresorption, effectively removes phosphate from the soil solution and renders it less available for plant uptake. And it is one of the principal reasons why phosphorus is often the most limiting nutrient for plant growth in many temperate soils. The potassium dynamics of temperate soils are intimately connected to the mineralogy of the clay fraction, particularly the abundance and type of 2:1-layer silicate minerals present. Potassium exists in the soil in several distinct pools, including the structural potassium locked within the crystal lattices of primary minerals such as feldspars and micas, the fixed or non-exchangeable potassium trapped in the interlayer spaces of a light and partially weathered micas, the exchangeable potassium held on the cation exchange sites of clay minerals and organic matter, and the dissolved potassium present in the soil solution. The release of potassium from the structural and fixed pools to the exchangeable and solution pools occurs through the slow weathering and transformation of potassium-bearing minerals, a process that can be accelerated by the activities of plant roots and mycorrhizal fungi, which secrete organic acids and other compounds that promote mineral dissolution. In soils rich in alite and vermiculite, the fixation of potassium in the interlayer spaces of these minerals can sometimes exceed the rate of release, leading to a net depletion of plant-available potassium despite an apparently abundant total supply. The calcium and magnesium content of temperate soils is largely determined by the nature of the parent material and the degree to which these elements have been leached from the soil profile by percolating water over the course of soil development. In soils derived from limestone, dolomite, or other calcareous parent materials, calcium and magnesium are typically present in abundance, maintaining the soil pH in the neutral to slightly alkaline range and supporting high levels of biological activity and nutrient cycling. In contrast, soils developed on siliceous parent materials in humid climates tend to lose calcium and magnesium relatively rapidly through leaching, leading to progressive acidification and a decline in base saturation over time. The rate of base cation loss varies depending on a number of factors, including the annual precipitation, the permeability of the soil, the cation exchange capacity, and the rate at which base cations are released from weathering minerals. Studies conducted in temperate forest ecosystems have measured calcium leaching rates ranging from approximately 5 to 50 kilograms per hectare per year depending on the site conditions, with the highest rates occurring in regions with high precipitation and sandy, freely draining soils. The micronutrient elements, including iron, manganese, zinc, copper, boron, molybdenum, and chlorine, are required by plants in much smaller quantities than the macronutrients, but are no less essential for normal growth and development. The availability of these elements in temperate soils is governed by a complex interplay of factors including pH, redox potential, organic matter content, and the presence of specific minerals and mineral coatings that can adsorb or release micronutrient ions. Iron and manganese, for instance, exist in the soil in both oxidized and reduced forms, with their solubility and availability being strongly dependent on the redox conditions prevailing in the soil. Under well-aerated, oxidizing conditions, iron and manganese are present primarily as insoluble oxides and oxyhydroxides, and their availability to plants may be limited even when their total concentrations in the soil are high. Under waterlogged, reducing conditions, however, these elements are converted to their more soluble reduced forms, and their concentrations in the soil solution can increase dramatically, sometimes to levels that are toxic to sensitive plant species. The physical structure of temperate soils, encompassing the arrangement of solid particles and pore spaces into a three-dimensional architecture, is a property that reflects the combined influence of texture, mineralogy, organic matter content, biological activity, and management history. Soil structure is typically described in terms of the shape, size, and strength of the aggregates or PEDs into which the soil mass naturally divides, with common structural types including granular, blocky, prismatic, columnar, and platy forms. The A-horizons of temperate soils under natural vegetation typically exhibit a granular structure in which small, roughly spherical aggregates ranging from 1 to 10 millimeters in diameter create an open, porous arrangement that facilitates the movement of water, air, and roots through the soil. This granular structure is maintained by a combination of biological and chemical binding agents, including fungal hyphae, bacterial polysaccharides, fine roots, and the organomineral complexes formed by the interaction of humic substances with clay minerals and metal oxides. The B horizons of temperate soils, lying beneath the A horizon and above the relatively unweathered C horizon, often display a blocky or prismatic structure that reflects the influence of clay accumulation, wetting and drying cycles, and the orientation of soil particles along planes of weakness. In soils where significant amounts of clay have been translocated from the A horizon to the B horizon by the process of alluviation, thin coatings of oriented clay particles, known as clay films or argillans, can be observed on the surfaces of structural aggregates and lining the walls of pores and root channels. These clay films, which are visible to the naked eye as shiny, smooth coatings on PED faces, are diagnostic features of the argillic horizon. A subsurface horizon defined by a significant increase in clay content relative to the overlying alluvial horizon. The presence of an argillic horizon is one of the key criteria used to classify soils as alpha sols in the USDA taxonomy, a soil order that encompasses many of the moderately weathered, base-rich soils found under deciduous forests in the temperate regions of North America, Europe, and Asia. The water-holding characteristics of temperate soils are directly related to the distribution of pore sizes within the soil matrix, which in turn is determined by the soil texture, structure, and organic matter content. The total porosity of a typical temperate soil, defined as the fraction of the soil volume occupied by pore spaces rather than solid particles, generally falls in the range of 40 to 60%, with sandy soils tending toward the lower end of this range and clay soils and well-aggregated loams toward the higher end. However, the total porosity alone does not fully describe a soil's water-holding behavior. Equally important is the distribution of pore sizes, because pores of different sizes retain water at different tensions and release it at different rates. Large pores, known as macropores, drain rapidly under the influence of gravity and are primarily responsible for soil aeration and the rapid transmission of water during heavy rainfall events. Smaller pores, known as micropores, retain water against the pull of gravity through capillary forces and serve as the primary reservoir of plant-available water between rainfall or irrigation events. The concept of plant-available water, defined as the difference between the field capacity and the permanent wilting point, is one of the most practically important soil properties for agriculture and ecology in temperate regions. Field capacity, which corresponds approximately to a soil water tension of negative 33 kilopascals, represents the maximum amount of water that a soil can hold against gravitational drainage after being thoroughly wetted. The permanent wilting point, corresponding to a soil water tension of approximately negative 1500 kilopascals, represents the lower limit of water availability, below which most plant roots can no longer extract water from the soil at a rate sufficient to prevent permanent wilting. The plant available water capacity of a soil depends primarily on its texture, with loamy soils generally offering the highest values, typically in the range of 150 to 200 millimeters per meter of soil depth, and sandy and heavy clay soils offering somewhat lower values due to their respective predominance of very large pores that drain freely and very small pores that hold water too tightly for plant extraction. The biological component of temperate soils encompasses an extraordinarily diverse community of organisms ranging in size from microscopic bacteria and archaea to visible invertebrates such as earthworms, insects, and mites. A single gram of temperate forest or grassland soil may contain billions of individual bacteria belonging to thousands of distinct species, along with hundreds of meters of fungal hyphae, millions of protozoa, and tens of thousands of nematodes. This soil biota plays a central role in virtually every process occurring in the soil, including the decomposition of organic matter, the cycling of nutrients, the formation and stabilization of soil aggregates, the suppression of plant pathogens, and the weathering of minerals. The composition and activity of the soil biological community are strongly influenced by the physical and chemical properties of the soil, including its pH, moisture content, temperature, organic matter quality and quantity, and mineral nutrient status, creating a complex web of feedbacks between the biotic and abiotic components of the soil system. Earthworms, among the most conspicuous and ecologically important members of the soil fauna in temperate regions, have been the subject of scientific study since at least the time of Charles Darwin, who published his final book, The Formation of Vegetable Mold Through the Action of Worms, in 1881. Darwin recognized that earthworms play a fundamental role in soil formation and maintenance through their burrowing and feeding activities, which serve to mix organic matter with the mineral soil, create channels for water infiltration and root growth, and bring material from deeper horizons to the surface. Modern research has confirmed and greatly extended Darwin's observations, demonstrating that earthworm activity can increase soil porosity by 10 to 30%, enhance water infiltration rates by factors of 2 to 6, and accelerate the turnover of plant litter and the release of plant-available nutrients. The population density of earthworms in temperate soils varies widely depending on the soil type, vegetation, climate, and management, but values in the range of 100 to 400 individuals per square meter are typical for productive grassland and deciduous forest soils, with the biomass of the earthworm community sometimes exceeding that of all other soil animals combined. The mycorrhizal fungi represent another critically important biological component of temperate soils, forming mutualistic associations with the roots of the vast majority of terrestrial plant species. In temperate forests, the dominant mycorrhizal type is the ectomycorrhiza, in which fungal hyphae form a dense sheath around the fine roots and penetrate between the outer cortical cells to create a network of intercellular hyphae known as the Hardig net. The ectomycorrhizal fungi, which include many familiar mushroom-forming species in the genera Amanita, Boletus, Rusula, and Lactarius, extend their hyphae far into the surrounding soil, effectively increasing the absorptive surface area of the root system by orders of magnitude and enhancing the plant's ability to acquire phosphorus, nitrogen, and water from the soil. In temperate grasslands and many herbaceous plant communities, the arbuscular mycorrhizae, formed by fungi in the phylum Glomeromycota, are the predominant type, with the fungal hyphae penetrating directly into the root cortical cells and forming branched structures called arbuscules that serve as sites of nutrient exchange between the plant and the fungus. The seasonal dynamics of temperate soils add yet another layer of complexity to the already intricate picture of soil composition and mineral distribution. In regions with cold winters, the annual cycle of freezing and thawing exerts a powerful influence on soil physical properties, particularly the structure and porosity of the surface horizons. When soil water freezes, it expands by approximately 9% in volume, and the growth of ice crystals in the soil pores can physically disrupt aggregates, displace soil particles, and create new cracks and fissures that alter the soil's hydraulic properties. The depth to which freezing penetrates into the soil depends on the severity and duration of the cold period, the thermal properties of the soil, the depth of snow cover, and the moisture content of the soil at the time of freezing. In the northern parts of the temperate zone, frost penetration depths of 50 to 100 centimeters or more are common, while in milder temperate climates, freezing may be confined to the upper few centimeters or may not occur at all. The spring thaw in cold temperate regions triggers a cascade of physical, chemical, and biological processes that profoundly affect the soil environment. As the ice in the soil melts, the released water, combined with snow melt infiltrating from the surface, can temporarily saturate the upper horizons, creating conditions favorable for the reduction of iron and manganese and the mobilization of dissolved organic matter and nutrients. The pulse of available water and nutrients, coupled with the gradual warming of the soil, stimulates a burst of microbial activity and nutrient mineralization that is often reflected in a flush of plant growth in the weeks following snowmelt. This spring flush of nutrient availability has been documented in numerous studies across the temperate zones and is considered an important mechanism for synchronizing nutrient supply with the period of most active plant uptake, thereby minimizing nutrient losses through leaching and denitrification. The geography of soil distribution across the temperate biomes of the world reveals a set of broad patterns that reflect the interplay of climate, vegetation, parent material, and time on a continental scale. In the humid temperate regions of eastern North America, for instance, a latitudinal gradient of soil types can be traced from the spodosols of the northern coniferous forests through the alphasols of the mixed deciduous forests to the ultisols of the warm, humid southeast. This gradient corresponds to a progressive increase in the intensity of chemical weathering and leaching from north to south, driven primarily by the increase in mean annual temperature and the associated acceleration of mineral dissolution, organic matter decomposition, and clay mineral transformation. The spodosols of northern New England, the upper Great Lakes region, and eastern Canada are developed primarily on sandy glacial deposits under coniferous and mixed forests, and they are characterized by the strong podzolization process described earlier, with prominent alluvial and alluvial horizons and an overall acidic, nutrient-poor chemical status. Moving southward into the deciduous forest belt of the central and mid-Atlantic states, the alphasols predominate, developed on a wider variety of parent materials including glacial till, loess, limestone residuum, and various alluvial and colluvial deposits. These soils are characterized by the presence of an argillic horizon enriched in alluviated clay, a moderate to high base saturation reflecting the continued input of base cations from the weathering of feldspars and other primary minerals, and a horizon that, while typically less organic rich than the molic epipedon of grassland soils, still contains sufficient organic matter to support a diverse and active biological community. The alphasols of the temperate deciduous forests represent a kind of intermediate stage in the continuum of soil development, more weathered than the inceptisols and anisols of recently deposited or shallow substrates, but less weathered than the ultisols and oxasols of the warm, humid tropics. The ultisols, which dominate the landscape of the southeastern United States from Virginia and the Carolinas southward through Georgia, Alabama, and Mississippi, represent the next stage along this weathering continuum. These soils, like the alpha soils, possess an argillic horizon enriched in clay, but they differ in having a base saturation of less than 35% in the lower part of the argillic horizon, reflecting the more intense leaching of base cations that has occurred under the warmer, wetter climate of the southeast. The clay mineral assemblage of the ultisols is typically dominated by kaolinite, with lesser amounts of vermiculite and hydroxy-interlayered vermiculite, and the iron oxide fraction is more abundant and better crystallized than in the alpha sols to the north. The red and yellow colors that characterize many ultisols in the southeast are attributable to the abundance of hematite and goethite, respectively, with the relative proportions of these two minerals being influenced by factors such as drainage, organic matter content, and the temperature and moisture regime of the soil. In the interior of the North American continent, west of the deciduous forest belt and east of the Rocky Mountains, the mollysols of the Great Plains represent a fundamentally different pathway of soil development, one driven by the unique combination of a subhumid to semi-arid climate and a dense cover of perennial grasses. The thick, dark horizon of these grassland soils, enriched with organic matter by the annual turnover of grass roots and surface litter, is the defining feature of the mollysol order and one of the most visually distinctive soil horizons found anywhere in the world. The organic matter content of the mollic epipedon typically ranges from 3 to 6% in the drier western portions of the Great Plains to 6 to 12% or more in the wetter eastern tallgrass prairie region, with the total organic carbon stocks in the upper meter of soil reaching values of 100 to 200 megagrams per hectare in the most productive grassland soils. The mineral composition of the Great Plains mollysols reflects the calcareous glacial and glacial parent materials that cover much of the region, with calcium carbonate accumulations commonly found at depths of 50 to 100 centimeters in the drier western soils, forming a diagnostic calcic horizon that is characteristic of soils developed under conditions of limited leaching. The temperate grassland soils of other continents show broadly similar characteristics to those of the Great Plains, though with regional variations reflecting differences in parent material, climate, and vegetation composition. The Chernozems of the Ukrainian and Russian steppe, recognized as some of the most fertile soils in the world since at least the time of Dokuchev's pioneering studies in the 1870s and 1880s, are remarkably similar to the mollysols of the Great Plains in their deep, dark, organic-rich horizons and their generally high base saturation and favorable physical properties. The Chernozems typically develop on thick deposits of loess, a wind-blown silt that was deposited across much of the Eurasian steppe during the Pleistocene glaciations, and their clay mineral assemblage is dominated by a light and smectite, reflecting the relatively moderate degree of weathering that has occurred under the continental climate of the region. The pampas of Argentina support similar grassland soils, classified as mollysols or phaeosms depending on the taxonomic system used, developed on loess and loess-like sediments under a temperate climate with warm summers and mild winters. The temperate forests of Western Europe present yet another variation on the theme of soil development in the temperate zones, one that has been profoundly modified by thousands of years of human land use and management. The natural soil cover of Western Europe, prior to the extensive deforestation and agricultural development that began in the Neolithic period and accelerated through the medieval era, consisted of a complex mosaic of soil types reflecting the diversity of parent materials, climates, and vegetation types found across the region. The soils of the Atlantic coastal regions, from Portugal and western France northward through the British Isles and into Scandinavia, developed under the influence of a mild, humid oceanic climate characterized by moderate temperatures, abundant and evenly distributed rainfall, and a relatively long growing season. Under these conditions, the dominant soil-forming processes include the leaching of base cations, the translocation of clay and organic matter down the profile, and the development of a characteristic brown or yellowish-brown B horizon, enriched in iron oxyhydroxides and, in many cases, alluviated clay. The brown earth soils, known as cambisols in the World Reference Base for Soil Resources System or inceptisols in the USDA taxonomy, are among the most widespread soil types in the temperate regions of Western Europe, occupying large areas under both forest and agricultural land use. These soils are characterized by a relatively simple profile consisting of an A horizon with moderate organic matter content overlying a BW horizon that shows evidence of structural development and mineral weathering but lacks the strong horizon differentiation seen in more developed soil types such as the alphasols or spodosols. The clay mineral assemblage of the brown earths typically includes a mixture of alite, vermiculite, and chlorite, often with minor amounts of smectite and kaolinite, reflecting the intermediate degree of weathering that characterizes these soils. The pH values of Western European brown earths generally fall in the range of 5 to 6.5, with somewhat higher values in soils developed on calcareous parent materials and lower values in soils on acidic substrates. The loess-derived soils of Central Europe, found extensively in Germany, Belgium, northern France, Poland, and the Czech Republic, represent some of the most agriculturally productive soils in the continent and have been cultivated almost continuously since the earliest Neolithic farming communities settled the region approximately 7,000 years ago. These soils, typically classified as luvisols in the World Reference Base or alphasols in the USDA taxonomy, have developed on deposits of wind-blown silt that range in thickness from less than 1 meter to more than 20 meters in some areas. The uniform, silt-dominated texture of the loess parent material gives rise to soils with excellent water-holding capacity, good natural drainage, and a well-developed structure that is readily maintained under careful agricultural management. The clay mineral assemblage is dominated by alite and smectite, with the smectite fraction being particularly important for the cation exchange capacity and nutrient-holding ability of these soils. The podzolic soils of northern Europe, developed under the boreal and northern temperate forests of Scandinavia, Finland, and northern Russia, represent the extreme end of the leaching and acidification continuum in the European context. These soils, classified as podzols in the World Reference Base or spodosols in the USDA taxonomy, develop under the strongly acidifying influence of coniferous litter and the cool, humid climate that characterizes the northern margins of the temperate zone. The profile morphology of the northern European podzols closely resembles that of their North American counterparts, with a thick organic O horizon, a thin and often intermittent A horizon, a conspicuous bleach D horizon, and a dark-colored BHS or BS horizon enriched in translocated organic matter, iron, and aluminum. The parent materials for these soils are typically glacial sands and gravels deposited during the retreat of the Scandinavian ice sheet at the end of the last glaciation, approximately 10,000 to 12,000 years ago. And the coarse texture of these deposits facilitates the rapid downward movement of water and dissolved organic acids that drives the podzolization process. The soils of the southern hemisphere's temperate regions, though less extensively studied than their northern hemisphere counterparts, display many of the same general features and developmental processes while also exhibiting some distinctive characteristics related to the unique geological and climatic histories of the southern continents. In southeastern Australia, the temperate soils encompass a wide range of types, from the deep, red ferrosols developed on basaltic parent materials in the volcanic districts of Victoria and South Australia to the pale, sandy podosols of the coastal heathlands and the dark, cracking vertisols of the inland clay plains. The ferrosols, which are among the most productive agricultural soils in Australia, are characterized by high clay contents, strong structural development, and abundant iron oxide minerals that give the soils their characteristic red color. The clay mineral assemblage of these soils is dominated by kaolinite and halloysite, reflecting the intense weathering that the basaltic parent materials have undergone under the relatively warm and seasonally moist climate of southeastern Australia. In New Zealand, the temperate soils reflect the country's complex geological history, diverse topography, and the influence of volcanic activity, which has contributed significant quantities of tephra, or volcanic ash, to the soil parent material over the past several 100,000 years. The soils developed on tephra deposits, classified as andisols in the World Reference Base or andisols in the USDA taxonomy, possess a number of unique properties that distinguish them from soils formed on other types of parent material. The rapid weathering of the volcanic glass and poorly crystalline minerals in the tephra produces large quantities of allophane and amygdalite, two short-range order aluminosilicate minerals with extremely high surface areas and reactive properties. These minerals give andisols their characteristic low bulk density, high water holding capacity, high phosphate retention, and dark color, properties that have important implications for both agriculture and the environment. The allophanic soils of New Zealand's central North Island, for example, can hold several times their own weight in water and have bulk densities as low as 0.5 to 0.7 grams per cubic centimeter, compared to typical values of 1.1 to 1.5 grams per cubic centimeter for most mineral soils. The temperate soils of southern South America, particularly those of the Argentine Pampas, Patagonia, and central Chile, present still another set of variations on the temperate soil theme. The Pampean mollysols, as mentioned earlier, are developed primarily on loess and loess-like sediments and share many characteristics with the Chernozems of the Eurasian steppe and the mollysols of the North American Great Plains. However, the Pampean soils exhibit some distinctive features related to the specific climatic and geological conditions of the region, including a pronounced east-west gradient in organic matter content and leaching intensity that mirrors the decline in annual precipitation from more than 1,000 millimeters in the eastern Pampas to less than 500 millimeters in the western, semi-arid zone. The soils of Patagonia, by contrast, are developed under a cold, windy, and arid climate that limits both chemical weathering and biological activity, resulting in relatively young, poorly developed soils classified as aridosols or entosols, with low organic matter contents, alkaline pH values, and often significant accumulations of soluble salts and calcium carbonate. The role of glaciation in shaping the soils of the temperate zones cannot be overstated, as the repeated advance and retreat of continental ice sheets during the Pleistocene epoch, spanning roughly the past 2.6 million years, has profoundly influenced the parent materials, topography, and drainage patterns across vast areas of North America, Europe, and parts of South America and Australasia. In the regions that were directly covered by glacial ice, the pre-existing soils were stripped away entirely and replaced by deposits of glacial till, a heterogeneous mixture of clay, silt, sand, gravel, and boulders deposited directly by the ice, or by various types of glaciofluvial, glaciolacustrine, and aeolian sediments laid down by meltwater streams, glacial lakes, and wind in the periglacial environment surrounding the ice margins. The soils that have developed on these glacial deposits since the retreat of the last ice sheets, approximately 10,000 to 15,000 years ago in most temperate regions, are therefore relatively young in pedological terms, and many of them are still in the early to intermediate stages of profile development. The glacial till that forms the parent material for vast areas of soil in the northern United States, southern Canada, Scandinavia, the British Isles, and northern Germany and Poland varies considerably in its composition depending on the nature of the bedrock over which the glacier moved. In regions underlain by crystalline igneous and metamorphic rocks, such as the Canadian Shield and the Scandinavian Shield, the glacial till tends to be sandy to loamy in texture with a mineral assemblage dominated by quartz, feldspars, and various ferromagnesian minerals, and the soils developed on this material are typically acidic, relatively low in nutrients, and prone to podzolization under coniferous forest cover. In regions where the glacier overrode sedimentary rocks such as limestone, dolomite, and shale, the till is often finer in texture and more calcareous, and the resulting soils tend to be more fertile, less acidic, and more likely to develop as alphasols or molysols rather than spodosols. The glacial tills of the American Midwest, for example, are derived largely from Paleozoic limestones and shales, and have given rise to some of the most productive agricultural soils in the world, characterized by silt loam to clay loam textures, high base saturation, and favorable physical properties for root growth and water retention. The loess deposits that blanket extensive areas of the temperate zones are another legacy of the Pleistocene glaciations, formed by the deflation and wind transport of fine silt particles from the barren, unvegetated surfaces of glacial outwash plains, braided river floodplains, and exposed lake beds. The thickness of loess deposits varies from a few centimeters in areas far from the source to more than 30 meters in some locations along the major river valleys of the Mississippi-Missouri system in North America and the Rhine-Danube system in Europe, as well as in the extensive loess plateau of northern China, which contains some of the thickest and most continuous loess deposits in the world. The mineralogy of loess is dominated by quartz and feldspars in the silt fraction, with lesser amounts of micas, carbonates, and heavy minerals, and the clay fraction typically consists of a mixture of a light, smectite, and chlorite derived from the weathering of these primary minerals. The remarkable uniformity of loess in both texture and mineralogy makes it an ideal parent material for soil development, and the soils formed on loess tend to be among the most homogeneous and predictable in their properties of any soils in the temperate zones. The influence of topography on soil composition and mineral distribution in temperate landscapes operates through its effects on water movement, erosion and deposition, microclimate, and the local redistribution of soil materials across the landscape. On sloping terrain, the downslope movement of water through both surface runoff and subsurface lateral flow creates a systematic variation in soil properties from the summit to the foot slope positions, a pattern that soil scientists refer to as a catena or toposequence. Soils on the upper slope positions or shoulders tend to be shallower, better drained, and more oxidized than soils in the lower positions, owing to the enhanced erosion and water shedding that occurs on convex slope segments. Soils in the mid-slope or back-slope positions typically show intermediate characteristics, while soils in the foot slope and toe slope positions at the base of the slope tend to be deeper, wetter, and more enriched in fine-textured sediments, organic matter, and dissolved nutrients transported from upslope by water flow. This catenary variation in soil properties has been documented in numerous studies across the temperate zones and has important implications for the spatial distribution of minerals, nutrients, and soil carbon at the landscape scale. In a typical catena on glacial till in the upper Midwest of the United States, for example, the summit soils may be well-drained molysols with moderate organic matter content and a clay mineral assemblage dominated by a light, while the footslope soils are poorly drained mollysols or coals with higher organic matter content, greater clay content, and a more smectite-rich clay assemblage, reflecting the preferential transport and accumulation of fine particles and weathering products in the lower landscape positions. The transition from well-drained to poorly drained conditions along the Katina is also reflected in the iron mineralogy of the soil, with goethite and hematite predominating in the oxidized upslope soils and reduced iron phases, including ferrous sulfides and siderite appearing in the waterlogged soils of closed depressions and drainage ways. The temporal dimension of soil development in temperate regions is perhaps best illustrated by the concept of the soil chronosequence, a series of soils of different ages, but similar parent material, climate, topography, and vegetation, which allows pedologists to trace the progressive changes in soil properties that occur as weathering and pedogenesis proceed over time. Studies of soil chronosequences on glacial moraines, river terraces, and volcanic deposits in temperate regions have revealed a consistent set of developmental trends that include the gradual deepening of the soil profile, the progressive weathering and transformation of primary minerals to secondary clay minerals and oxides, the accumulation and redistribution of organic matter, the leaching of soluble salts and carbonates, the translocation of clay and iron from upper to lower horizons, and the gradual decline in pH and base saturation as base cations are removed by leaching faster than they are released by mineral weathering. One of the most thoroughly studied soil chronosequences in the temperate zone is the series of soils developed on the glacial moraines of the Sierra Nevada in California, where surfaces ranging in age from a few hundred years to more than 3 million years have been preserved by the semi-arid climate and stable tectonic conditions of the region. On the youngest surfaces, the soils are little more than thin accumulations of slightly weathered mineral grains with minimal profile development and negligible clay formation. On surfaces of intermediate age, ranging from approximately 10,000 to 100,000 years, the soils show progressive development of an argillic horizon enriched in clay minerals including kaolinite, halloysite, and smectite, along with increasing accumulations of iron oxides in the B horizon. On the oldest surfaces, exceeding 1 million years in age, the soils have evolved into deeply weathered ultisols with thick, bright red argillic horizons dominated by kaolinite and iron oxides, representing the end stage of soil development under the prevailing climatic conditions. The management and conservation of temperate soils in the modern era has become a subject of increasing concern and scientific attention, driven by the recognition that these soils, which support a disproportionate share of the world's agricultural production and harbor vast reserves of organic carbon, are being degraded at an alarming rate by erosion, compaction, nutrient depletion, acidification, contamination, and the loss of organic matter. The conversion of native grasslands and forests to cropland, which has occurred across millions of hectares of the temperate zones over the past several centuries, has typically resulted in a significant decline in soil organic matter content, often amounting to a loss of 20 to 50% of the original organic carbon stocks within the first few decades of cultivation. This loss of organic matter has cascading effects on soil structure, water holding capacity, nutrient cycling, and biological activity, creating a positive feedback loop in which the degradation of soil physical and biological properties further accelerates the decomposition and loss of remaining organic matter. Erosion by water and wind is another major threat to temperate soils, particularly on sloping agricultural land and in regions with intense or concentrated rainfall. The rate of soil erosion on cultivated land in temperate regions has been estimated at anywhere from 5 to more than 100 metric tons per hectare per year, depending on the soil type, slope, rainfall characteristics, crop type, and management practices, with the higher rates typically associated with clean-tilled row crops on steep slopes with little or no conservation measures in place. These erosion rates far exceed the rate of soil formation from the weathering of parent material, which is generally estimated at somewhere between 0.1 and 2 metric tons per hectare per year in temperate environments, meaning that the soil resource is being depleted much faster than it can be replenished through natural processes. The recognition of this imbalance has led to the development and widespread adoption of conservation practices such as contour farming, strip cropping, terracing, cover cropping, and no-till agriculture, all of which are designed to reduce the rate of soil erosion and maintain the long-term productivity of the soil resource. The carbon sequestration potential of temperate soils has emerged as a particularly active area of research in recent years, driven by the realization that soils contain approximately 2 to 3 times as much carbon as the atmosphere, and that relatively modest changes in soil carbon stocks could have significant implications for the global carbon cycle and climate change. The soils of the temperate zones are estimated to contain approximately 400 to 500 petagrams of organic carbon in the upper 1 meter, with the mollysols of the temperate grasslands accounting for a disproportionately large share of this total due to their deep, carbon-rich mollic epipedons. Strategies for increasing soil carbon sequestration in temperate agricultural systems include the adoption of no-till or reduced tillage practices, the use of cover crops and diverse crop rotations, the application of organic amendments such as compost and biochar, the restoration of degraded grasslands and forests, and the management of grazing intensity to optimize root growth and organic matter inputs. While the potential for soil carbon sequestration is not unlimited, and the rates of carbon accumulation tend to decline as soils approach a new equilibrium state, the available evidence suggests that improved soil management could contribute meaningfully to the mitigation of greenhouse gas emissions while simultaneously improving soil health and agricultural productivity. The study of soil mineralogy and composition in temperate biomes continues to advance through the application of increasingly sophisticated analytical techniques, including X-ray diffraction, scanning electron microscopy, transmission electron microscopy, energy dispersive X-ray spectroscopy, nuclear magnetic resonance spectroscopy, and various forms of synchrotron-based spectroscopy that allow researchers to probe the structure and chemistry of soil minerals at the nanometer scale. These techniques have revealed previously unsuspected complexity in the mineral assemblages of temperate soils, including the widespread occurrence of mixed-layer clay minerals with interstratified structures that do not correspond neatly to any of the standard clay mineral categories. The presence of nanoscale iron and aluminum oxide particles with surface areas and reactivities far exceeding those of their bulk crystalline counterparts, and the intimate association of organic molecules with mineral surfaces at scales that are invisible to conventional optical microscopy. The integration of these nanoscale observations with the macro-scale patterns of soil distribution and behavior across temperate landscapes represents one of the most exciting and intellectually challenging frontiers in modern soil science, a field that, for all its quiet reputation, continues to yield discoveries of fundamental importance for our understanding of the Earth's surface and the ecosystems it supports. The trace element geochemistry of temperate soils provides yet another dimension through which the mineral composition and pedogenic history of these soils can be understood, and the distribution of elements such as chromium, nickel, cobalt, vanadium, strontium, barium, zirconium, and the rare earth elements across soil profiles and landscapes has been the subject of extensive investigation by geochemists and pedologists working in temperate environments around the world. Trace elements in soils are derived primarily from the weathering of the parent material, with additional inputs from atmospheric deposition, biological cycling, and in some cases anthropogenic contamination. And their distribution within the soil profile is controlled by a complex set of processes including selective dissolution, precipitation, adsorption, complexation with organic matter, and incorporation into the crystal structures of secondary minerals. Zirconium and titanium, for example, are present in soils almost exclusively in the form of highly resistant accessory minerals such as zircon and rutile, which are virtually insoluble under normal soil conditions and therefore tend to accumulate in relative terms as other, more soluble minerals are removed by weathering. For this reason, the ratios of zirconium or titanium to more mobile elements are commonly used by soil scientists as indices of the degree of weathering and leaching that a soil has undergone, with higher ratios indicating more advanced stages of pedogenic development. The rare earth elements, a group of 15 chemically similar elements from lanthanum to lutetium, plus the closely related elements scandium and yttrium, have attracted particular attention in recent decades as tracers of soil-forming processes and indicators of parent material provenance. In unweathered rocks, the rare earth elements occur primarily in accessory minerals such as monazite, apatite, xenotime, and alunite, as well as in trace amounts substituted into the crystal lattices of more abundant minerals such as feldspars, pyroxenes, and amphiboles. As these minerals weather in the soil environment, the rare earth elements are released into the soil solution, where they may be adsorbed onto clay mineral surfaces, complexed with organic matter, precipitated as phosphate or carbonate phases, or leached from the soil profile in dissolved form. The patterns of rare earth element fractionation that develop during soil formation can provide valuable information about the mechanisms and intensity of weathering, the role of organic complexation in element transport, and the relative importance of different mineral phases as sources and sinks for these elements within the soil. The silicon cycle in temperate soils, though less commonly discussed than the cycles of carbon, nitrogen, and phosphorus, is nonetheless of considerable importance for understanding the mineral dynamics of these soils and their interactions with the broader Earth system. Silicon is the second most abundant element in the Earth's crust after oxygen, and it is present in soils primarily in the form of silicate minerals, which together constitute the bulk of the mineral fraction. The weathering of silicate minerals releases dissolved silicon in the form of silicic acid with the formula H4CO4 into the soil solution, where it can be taken up by plant roots, adsorbed onto aluminum and iron oxide surfaces, precipitated as amorphous silica or secondary aluminosilicate minerals, or leached from the soil profile and transported to streams, rivers, and ultimately the ocean. The rate of silicate weathering in temperate soils has been estimated at approximately 1 to 10 metric tons of silica per square kilometer per year, depending on the climate, lithology, and vegetation cover. And this process is recognized as one of the principal long-term sinks for atmospheric carbon dioxide through the consumption of CO2 in the weathering reactions. The role of plants in the silicon cycle of temperate soils is more significant than is often appreciated, as many plant species, particularly grasses, sedges, and horsetails, accumulate substantial quantities of silicon in their tissues in the form of microscopic bodies of hydrated amorphous silica known as phytoliths. These phytoliths, which take on distinctive shapes depending on the plant species and tissue type in which they form, are deposited in the soil when the plant material decomposes and can persist for thousands or even millions of years, providing a valuable record of past vegetation for paleoecologists and archaeologists. The dissolution of phytoliths in the soil releases biogenic silica back into the soil solution, creating a secondary source of dissolved silicon that supplements the primary input from mineral weathering. Studies of the silicon cycle in temperate grassland and forest ecosystems have shown that the biological recycling of silicon through plant uptake and phytolith dissolution can be several times larger than the input from mineral weathering, highlighting the importance of the biological component in driving the overall silicon dynamics of the soil-plant system. The aluminum geochemistry of temperate soils is closely intertwined with the processes of clay mineral weathering and formation, organic matter dynamics, and soil acidification that have been discussed throughout this account. Aluminum is released from the crystal lattices of feldspars, micas, and other primary aluminosilicate minerals as they weather in the soil environment. And the fate of this released aluminum depends strongly on the pH and organic matter content of the soil. In soils with pH values above approximately 5.5, most of the dissolved aluminum precipitates rapidly as aluminum hydroxide, AlOH3, or is incorporated into the structures of newly forming clay minerals, keeping the concentration of dissolved aluminum in the soil solution at very low levels. In more acidic soils, however, the solubility of aluminum increases dramatically, and dissolved aluminum species, including the toxic Al3+ ion and various hydroxoaluminum complexes, can accumulate in the soil solution at concentrations sufficient to inhibit root growth and impair the uptake of essential nutrients such as calcium, magnesium, and phosphorus. Aluminum toxicity is recognized as one of the most important constraints on plant growth in acid soils worldwide, and it is particularly problematic in the strongly acidic spodosols and degraded ultisols of the temperate zones. The manganese geochemistry of temperate soils exhibits many parallels with that of iron, as both elements undergo redox cycling between their oxidized and reduced forms in response to fluctuations in the soil moisture and oxygen status. Under well-aerated conditions, manganese is present in the soil primarily as insoluble manganese oxides, the most common of which include bernesite, lithophorite, and todorokite, which form dark-colored coatings, nodules, and concretions in many temperate soils. These manganese oxide minerals have remarkably high surface areas and strong oxidizing properties, and they play important roles in the sorption and transformation of trace metals, the oxidation of organic compounds, and the cycling of several other elements in the soil environment. Under waterlogged or otherwise reducing conditions, the manganese oxides dissolve and release soluble Mn2+ ions into the soil solution, which can then migrate through the soil and reprecipitate as oxides when they encounter more oxidizing conditions, creating the complex patterns of manganese accumulation and depletion that are characteristic of soils with fluctuating water tables. The sulfur cycle in temperate soils involves a complex series of transformations between organic and inorganic forms that are mediated primarily by soil microorganisms and that link the soil sulfur pool to the broader biogeochemical cycles of the atmosphere, hydrosphere, and biosphere. In most well-drained temperate soils, the majority of the total sulfur is present in organic forms, bound to carbon in the structures of amino acids, proteins, sulfolipids, and other organic compounds that constitute part of the soil organic matter. The mineralization of these organic sulfur compounds by soil bacteria and fungi releases inorganic sulfate, so 4,2-, into the soil solution, where it can be taken up by plant roots, adsorbed onto iron and aluminum oxide surfaces, leached from the soil profile, or reduced to sulfide under anaerobic conditions. The atmospheric deposition of sulfur, both as sulfur dioxide gas and as dissolved sulfate in rainfall, has historically been an important source of sulfur to temperate soils in industrialized regions. Though the implementation of clean air regulations in many countries over the past several decades has substantially reduced sulfur deposition levels in many areas. The physical weathering processes that affect temperate soils, while perhaps less chemically nuanced than the mineral transformations discussed above, are nonetheless essential for understanding the development and maintenance of the soil mantle across temperate landscapes. Frost weathering, the mechanical disintegration of rock and soil aggregates by the repeated freezing and thawing of water in pores and cracks, is particularly effective in the colder parts of the temperate zone and in mountainous areas where diurnal and seasonal temperature fluctuations regularly cross the freezing point. The expansion of water upon freezing generates pressures that can exceed the tensile strength of most rock types, progressively widening existing fractures and eventually breaking the rock into smaller fragments that are more susceptible to chemical weathering and incorporation into the soil. The effectiveness of frost weathering depends on a number of factors, including the frequency and magnitude of freeze-thaw cycles, the initial porosity and permeability of the rock, the degree of water saturation at the time of freezing, and the mineral composition and grain size of the rock, with fine-grained, porous, water-saturated rocks being the most susceptible to frost damage. Biological weathering, the breakdown of rock and minerals by the activities of living organisms, is another process that contributes to soil formation and mineral transformation in temperate environments. Plant roots, as they grow into cracks and fissures in the bedrock, exert mechanical pressures that can widen existing fractures and create new pathways for water infiltration and chemical weathering. The organic acids and chelating compounds secreted by roots and their associated mycorrhizal fungi further accelerate mineral dissolution by lowering the pH of the soil solution at the mineral surface and by forming soluble complexes with metal ions that would otherwise remain bound in the mineral lattice. Lichens, those remarkable symbiotic associations of fungi and algae that colonize bare rock surfaces in many temperate environments, are particularly effective biological weathering agents, producing a variety of organic acids including oxalic acid, citric acid, and various phenolic compounds that can dissolve silicate and carbonate minerals at rates significantly higher than those achieved by abiotic weathering processes alone. The interplay of all these physical, chemical, and biological processes over timescales ranging from years to millennia gives rise to the remarkable diversity of soil types and mineral assemblages found across the temperate biomes of the world. From the deep, dark mollysols of the continental grasslands to the bleached spotosols of the boreal forest margins, from the red, kaolinite-rich ultisols of the warm, humid subtropics to the allophanic andisols of the volcanic highlands. The soils of the temperate zones represent an extraordinary archive of environmental history and a vital foundation for terrestrial ecosystem function. Each handful of temperate soil contains within it a record of the geological, climatic, biological, and human influences that have shaped its development, written in the language of mineral grains, organic molecules, pore spaces, and living organisms. The patient decipherment of this record, through the methods of soil science, mineralogy, chemistry, and biology, remains one of the most quietly rewarding endeavors in all of earth science. a field in which the careful observation of the most ordinary material can yield insights of truly extraordinary depth and significance. Though one would be forgiven for finding the process rather soporific in its methodical thoroughness and unhurried attention to detail. And so the study continues, as soil scientists around the world persist in their meticulous cataloging of mineral phases and organic fractions, their careful measurement of cation exchange capacities and base saturation percentages, their patient excavation of soil pits, and their methodical description of horizon sequences. Each new study adds another small piece to the vast and ever-growing mosaic of knowledge about the composition and behavior of temperate soils, a mosaic that, while never complete, grows incrementally more detailed and more nuanced with each passing year. The minerals weather and transform, the organic matter accumulates and decomposes, the organisms burrow and digest, and the water percolates steadily downward through the profile, carrying dissolved ions and suspended particles on their slow journey toward the water table and beyond. It is a world of processes measured in millimeters and millennia, of changes so gradual that they are imperceptible to the casual observer, but so profound in their cumulative effects that they have shaped the landscapes and ecosystems of the temperate world in ways that we are only beginning to fully appreciate and understand. The thermal properties of temperate soils, encompassing their capacity to absorb, store, and conduct heat, represent another aspect of soil composition that has been studied with considerable attention by soil physicists and agronomists, particularly in regions where soil temperature plays a critical role in determining the timing and success of agricultural operations, the rate of organic matter decomposition, and the activity of soil organisms. The thermal conductivity of a soil, defined as the rate at which heat flows through a unit thickness of soil per unit temperature gradient, depends primarily on the mineral composition, the moisture content, the bulk density, and the relative proportions of solid, liquid, and gaseous phases within the soil matrix. Quartz, the most thermally conductive of the common soil minerals, has a thermal conductivity of approximately 7.7 watts per meter per Kelvin, compared to values of roughly 2 to 3 watts per meter per Kelvin for most other silicate minerals, and only 0.25 watts per meter per Kelvin for soil organic matter. As a result, sandy soils rich in quartz tend to warm up more quickly in the spring than clay soils or organic soils, a difference that can have important practical implications for the timing of seed germination and crop establishment in temperate agricultural systems. The heat capacity of soils, which determines the amount of energy required to raise the temperature of a given mass of soil by 1 degree, is similarly influenced by the mineral composition and moisture status of the soil. Water has a specific heat capacity of 4.18 joules per gram per Kelvin, roughly 5 times higher than that of most soil minerals, which means that wet soils require considerably more energy input to achieve the same temperature change as dry soils. This relationship has important consequences for the diurnal and seasonal temperature fluctuations experienced by temperate soils. with wet soils tending to show smaller amplitude temperature variations than dry soils of similar texture and mineral composition. The damping of temperature extremes in wet soils can be beneficial for soil organisms and plant roots, which may be sensitive to rapid temperature changes, but it can also delay the warming of the soil in spring, potentially reducing the length of the growing season in regions where soil temperature is a limiting factor for crop growth. The electrical properties of temperate soils, including their electrical conductivity, dielectric constant, and magnetic susceptibility, are additional physical parameters that reflect the mineral composition and chemical status of the soil, and that have found practical applications in areas ranging from precision agriculture to archaeological prospection. The electrical conductivity of a soil, which measures the ease with which an electric current can flow through the soil matrix, is determined primarily by the concentration of dissolved ions in the soil solution, the moisture content of the soil, and the clay content and mineralogy, with soils rich in smectite clays and dissolved salts showing the highest conductivities. In temperate agricultural settings, the spatial variation of soil electrical conductivity across a field can be measured rapidly and non-invasively using electromagnetic induction instruments, providing a surrogate measure of soil texture, moisture, and salinity that can be used to guide variable rate fertilizer application, irrigation management, and other precision farming practices. The magnetic susceptibility of soils, which reflects the concentration and type of iron-bearing minerals present, has been used extensively as a tool for mapping soil variation, detecting anthropogenic contamination, and reconstructing past environmental conditions from buried soil sequences. In most temperate soils, the magnetic susceptibility is dominated by the contribution of ferromagnetic minerals such as magnetite and magamite, which have magnetic susceptibilities several orders of magnitude higher than those of the antiferromagnetic and paramagnetic minerals that make up the bulk of the mineral fraction. The formation of secondary magnetite and magamite in soils occurs through a variety of pathways, including the thermal transformation of other iron oxides during burning, the biological reduction and oxidation of iron by magnetotactic bacteria, and the weathering of ferromagnesian silicate minerals under specific chemical conditions. The enhancement of magnetic susceptibility in the A horizons of many temperate soils, relative to the underlying B and C horizons, has been attributed to the pedogenic formation of ultrafine magnetite and magamite particles, and this enhancement signal has been widely used in paleoclimatic studies to reconstruct past variations in rainfall and temperature from less paleosol sequences in China, Europe, and elsewhere. The colloidal fraction of temperate soils, comprising particles smaller than 1 micrometer in diameter, includes not only the clay minerals and iron and aluminum oxides discussed earlier, but also a diverse assemblage of organic colloids, biogenic nanoparticles, and mixed organic mineral entities that play disproportionately important roles in the retention and transport of nutrients, contaminants, and dissolved organic matter within the soil profile. The surface chemistry of these colloidal particles, is characterized by the presence of both permanent and variable electrical charges that arise from isomorphous substitution within crystal lattices and from the protonation and deprotonation of surface functional groups, respectively. The permanent negative charge of smectite and vermiculite clays, which results from the substitution of lower Veloce cations such as magnesium and aluminum for higher Veloce cations such as aluminum and silicon in the mineral structure, is responsible for the high cation exchange capacity of soils rich in these minerals and accounts for their ability to retain and supply essential plant nutrients such as potassium, calcium, and magnesium. The variable charge component, which becomes increasingly negative as the pH rises and increasingly positive as the pH falls, is particularly important in the iron and aluminum oxide-rich soils of the warmer temperate regions and plays a critical role in the retention of anions such as phosphate, sulfate, and molybdate. The process of mineral neoformation, the creation of entirely new mineral phases from dissolved constituents in the soil solution, is an ongoing process in temperate soils that operates alongside the better-known processes of mineral weathering and transformation. The precipitation of calcium carbonate in the B and C horizons of semi-arid temperate soils, forming calcic and petrocalcic horizons, is one of the most widespread examples of mineral neoformation in the temperate zones and the morphology, mineralogy, and stable isotope composition of these pedogenic carbonates have been used extensively as paleoenvironmental indicators. In the early stages of calcic horizon development, the carbonate occurs as thin filaments, soft nodules, and coatings on the undersides of gravel clasts, but with increasing time and continued carbonate accumulation, these features coalesce into continuous layers and eventually into massive, indurated horizons known as petrocalcic horizons or caliche, which can attain thicknesses of several meters and contain carbonate concentrations exceeding 60% by weight. The precipitation of silica in temperate soils, while less common than carbonate precipitation, does occur in certain environments, particularly in the seasonally dry temperate regions of Australia, South Africa, and parts of South America, where the evaporative concentration of dissolved silica in the soil solution can lead to the formation of opaline silica cements and silcretes. These siliceous duocrusts, which can be extremely hard and resistant to erosion, form important landscape features in some temperate regions and have been the subject of considerable debate among geomorphologists regarding their mode of formation, the environmental conditions under which they develop, and their significance as indicators of past climate and landscape evolution. The silica in these formations is typically derived from the weathering of silicate minerals in the soil and saprolite, transported in dissolved form by percolating groundwater, and precipitated as amorphous or microcrystalline silica in response to changes in pH, temperature, or evaporation rate. The formation of iron-manganese concretions and nodules in temperate soils is another example of mineral neoformation that occurs widely in soils subject to periodic waterlogging and redox fluctuations. These concretions, which range in size from less than 1 millimeter to several centimeters in diameter, consist of concentric layers of iron and manganese oxides that have precipitated around a nucleus, which may be a mineral grain, a root fragment, or an existing concretion. The formation of these features requires alternating periods of reducing conditions, during which iron and manganese are mobilized in their soluble reduced forms, and oxidizing conditions, during which the dissolved metals precipitate as insoluble oxides, building up successive layers over time. The internal structure of soil concretions, which can be examined in thin section under a petrographic microscope, often reveals a complex history of growth, dissolution, and reprecipitation that reflects the fluctuating moisture and redox conditions experienced by the soil over periods of decades to millennia. The study of soil micromorphology, which involves the preparation and examination of undisturbed soil thin sections under polarized light microscopy, has contributed enormously to our understanding of the mineral composition, fabric, and pedogenic history of temperate soils. This technique, first developed by the German-born soil scientist Walter Kubina in the 1930s and subsequently refined by generations of researchers, allows the direct observation of mineral grains, clay coatings, organic residues, void spaces, and pedogenic features in their natural spatial relationships, providing information that cannot be obtained from bulk chemical or mineralogical analyses alone. In a typical micromorphological study of a temperate soil, the researcher might observe the orientation and distribution of clay particles around void walls and aggregate surfaces, the presence of phytoliths, charcoal fragments, and fungal spores within the organic fraction, the development of iron oxide nodules and manganese coatings, and the arrangement of sand and silt grains within the soil fabric. These observations, when interpreted in the context of the known soil-forming processes and environmental history of the site, can provide a remarkably detailed picture of the pedogenic transformations that have shaped the soil over its history. The discipline of soil geography, which seeks to understand and predict the spatial distribution of soil types and properties across landscapes and regions, draws upon all of the mineralogical, chemical, physical, and biological knowledge described in this account to construct maps and models that represent the three-dimensional complexity of the soil cover at various scales of resolution. The earliest systematic soil maps of temperate regions were produced in the late 19th and early 20th centuries by pioneers such as Dokuchev in Russia, Hilgard in the United States, and Raman in Germany, who recognized that the broad-scale distribution of soil types could be related to the zonal patterns of climate and vegetation that characterize the Earth's surface. These early zonal soil maps, while necessarily simplified and imprecise by modern standards, establish the conceptual framework that continues to underlie our understanding of soil distribution in the temperate zones, and the broad patterns they identified, such as the progression from podzols to brown earths to Chernozems across the climatic gradient from humid to subhumid conditions in the northern hemisphere, remain valid and useful as generalizations of the soil geographic reality. Modern soil mapping in temperate regions has been revolutionized by the advent of remote sensing, geographic information systems, digital terrain analysis, and geostatistical modeling techniques that allow soil properties to be predicted and mapped at much higher spatial resolutions and with much greater accuracy than was possible using the traditional manual survey methods. The emerging field of digital soil mapping, also known as predictive soil mapping or soil landscape modeling, uses quantitative relationships between measured soil properties and easily obtainable environmental covariates, such as terrain attributes derived from digital elevation models, satellite imagery, geological maps, and climate data, to predict the spatial distribution of soil properties across landscapes and regions. These digital soil mapping approaches have been applied with considerable success in temperate regions around the world, producing maps of soil texture, organic carbon content, pH, depth to bedrock, and other properties at resolutions ranging from tens of meters to hundreds of meters, and they hold great promise for improving our ability to manage and conserve the soil resources of the temperate zones in an era of rapid environmental change and increasing demand for food, fiber, and ecosystem services. And so the quiet work of characterizing and understanding the mineral composition and distribution of temperate soils continues, one soil pit, one thin section, one X-ray diffraction pattern at a time, building steadily toward a more complete and nuanced understanding of the materials that form the thin but vital skin of the Earth's terrestrial surface. The minerals continue their slow transformations. The organic matter continues its endless cycle of accumulation and decay. And the patient observers continue to document and interpret the patterns and processes that define these most familiar yet endlessly complex natural systems, finding in their unhurried investigation a satisfaction that needs no dramatic revelation or startling discovery to sustain it, only the steady accumulation of knowledge and the quiet appreciation of the extraordinary complexity hidden within the most ordinary handful of earth. The relationship between soil mineral composition and the vegetation communities that develop upon temperate soils is one of reciprocal influence, a slowly turning feedback loop in which the minerals shape the conditions for plant growth and the plants, in turn, modify the soil environment through their root activities, litter inputs, and effects on water and nutrient cycling. In the temperate deciduous forests of eastern North America, for example, the species composition of the canopy is often closely correlated with the underlying soil type, with sugar maple, basswood, and white ash favoring the relatively fertile. Well-drained alpha soils developed on calcareous till and loess, while red oak, chestnut oak, and various hickory species predominate on the more acidic, nutrient-poor ultisols and inceptisols derived from silicious parent materials. These vegetational differences, in turn, influence the rate and pathway of nutrient cycling in the soil. As the calcium-rich litter of sugar maple and basswood decomposes more rapidly and maintains higher soil pH and base saturation than the more recalcitrant, tannin-rich litter of oak and hickory, creating a positive feedback that tends to reinforce and perpetuate the initial differences in soil chemistry. The concept of nutrient limitation in temperate soils, which addresses the question of which mineral element or elements most constrain plant growth and ecosystem productivity in a given soil vegetation system, has been a central preoccupation of ecosystem ecologists working in temperate environments for many decades. Classical nutrient limitation theory holds that plant growth in most temperate terrestrial ecosystems is limited primarily by the availability of nitrogen, with phosphorus being the next most commonly limiting element. And this view has been supported by numerous fertilization experiments in which the addition of nitrogen to temperate forest and grassland soils has resulted in significant increases in plant biomass production. However, more recent research has revealed a more nuanced picture in which the nature and degree of nutrient limitation varies depending on the soil type, vegetation, climate, and stage of ecosystem development, and in which co-limitation by multiple nutrients, including not only nitrogen and phosphorus, but also potassium, calcium, magnesium, and various micronutrients, may be more common than single-element limitation. The weathering rates of silicate minerals in temperate soils have been the subject of extensive measurement and modeling efforts over the past several decades, driven in part by the recognition that mineral weathering plays a critical role in determining the long-term supply of base cations and other nutrients to forest ecosystems, and in part by the concern that the accelerated leaching of base cations caused by acid deposition may deplete soil nutrient reserves faster than they can be replenished by mineral weathering. Field-based estimates of mineral weathering rates in temperate soils have been obtained through a variety of approaches, including mass balance calculations that compare the inputs of base cations from atmospheric deposition and mineral weathering with the outputs in stream water and biomass uptake. The analysis of strontium isotope ratios in soil solutions and stream water to distinguish between atmospheric and weathering-derived inputs and the direct measurement of mineral surface recession rates using microscopic and interferometric techniques. These studies have yielded weathering rate estimates that span approximately 2 orders of magnitude, from less than 0.5 to more than 50 kilomoles of charge per hectare per year, depending on the climate, mineralogy, soil pH, and hydrological conditions, with the highest rates generally observed in soils with abundant weatherable minerals, high moisture flux, and acidic soil solutions. The buffering capacity of temperate soils against acidification, which is closely related to the mineral composition and cation exchange properties of the soil, determines the resilience of the soil vegetation system to inputs of strong mineral acids from atmospheric deposition or other sources. In soils with abundant weatherable minerals and high base saturation, the displacement and consumption of hydrogen ions by the release of base cations from mineral surfaces and exchange sites provides effective buffering that can maintain the soil pH within a range that is favorable for most plant species and soil organisms. As the base saturation declines and the supply of weatherable minerals is depleted, however, the soil progressively loses its buffering capacity and becomes increasingly vulnerable to acidification. With the pH dropping into ranges where aluminum toxicity, reduced nutrient availability, and impaired microbial activity can significantly degrade soil quality and ecosystem function. The critical loads concept, which defines the maximum level of acid deposition that a soil can tolerate without suffering long-term damage, has been widely used in environmental policy to set emission reduction targets for sulfur dioxide and nitrogen oxides, and the calculation of critical loads relies heavily on estimates of mineral weathering rates and base cation depletion as indicators of soil sensitivity to acid inputs. The pedogenic formation of iron oxide minerals in temperate soils follows pathways that are controlled by the local drainage conditions, organic matter chemistry, and the concentration and speciation of dissolved iron in the soil solution. In well-drained, oxidizing soil environments, the weathering of iron-bearing primary minerals such as biotite, hornblende, and augite releases ferrous iron into the soil solution, which is rapidly oxidized to the ferric state and precipitates initially as poorly crystalline ferrihydrite. This ferrihydrite, with its characteristic reddish-brown color and extremely high surface area, is a metastable phase that gradually transforms to the more crystalline goethite through a process of dissolution and reprecipitation that may take years to centuries depending on the temperature, pH, and the presence of inhibiting substances such as organic matter and silica. In some temperate soils, particularly those that experience warm, dry conditions during part of the year, the transformation of ferrihydrite may proceed not to goethite but to hematite, the other common iron oxide in soils, through a pathway that involves internal dehydration and structural rearrangement of the ferrihydrite precursor. The colors of temperate soils, which range from the near black of organic-rich mollisol A horizons through the full spectrum of browns, yellows, reds, and grays to the stark white of bleached spottisol E horizons, are determined primarily by the concentration and mineralogy of the iron oxides and the amount of organic matter present. Goethite, the most common iron oxide in temperate soils, produces yellow to yellowish-brown colors that deepen to dark brown at high concentrations. Hematite, when present, produces distinctive red to reddish-brown colors that mask the yellower hues of coexisting goethite even when hematite is present in relatively small amounts. Because hematite is a much more effective pigmenting agent than goethite on a per-unit mass basis. The gray and bluish-gray colors seen in poorly drained and waterlogged soils result from the reduction and removal of iron oxides by microbial activity under anaerobic conditions, leaving behind the inherent colors of the mineral matrix, which are typically dominated by the pale grays and whites of quartz and feldspar grains. The integration of all these mineralogical, chemical, physical, and biological observations into a coherent understanding of soil formation and distribution across the temperate biomes remains the central challenge and aspiration of pedological science. A challenge that is made all the more formidable by the extraordinary spatial variability of soils at every scale of observation. From the centimeter-scale heterogeneity of aggregate interiors to the continental-scale patterns of soil orders and great groups. At the largest scales, the distribution of temperate soil types follows the broad climatic and vegetational gradients that characterize the temperate zones, with the spotosols and histosols of the cold. Humid north giving way to the alphasols and inceptisols of the temperate forest belt, the mollisols and vertisols of the grassland interiors, and the iridosols and calcisols of the dry continental margins. At intermediate scales, the pattern is complicated by the effects of parent material, topography, and land use history, which can produce dramatic contrasts in soil properties over distances of meters to kilometers. And at the finest scales, the soil reveals its full microscopic complexity, with individual sand grains coated in films of iron oxide and organic matter, clay particles arranged in oriented domains around voids and root channels, and microbial colonies thriving in the thin films of water that cling to mineral surfaces in an environment that is simultaneously solid, liquid, and gaseous. This multi-scale complexity is part of what makes the study of temperate soil composition and mineral distribution such a quietly absorbing pursuit. One that rewards patient observation with an ever-deepening appreciation of the intricate relationships between the mineral, organic, and living components of the soil system. The soil, so often overlooked and undervalued, is in fact one of the most complex and dynamic natural systems on the planet, a system in which the products of geological, climatic, biological, and chemical processes are blended together in combinations that are unique to each site and that change continuously, if imperceptibly, over time. The minerals that compose the bulk of any temperate soil, from the sturdy quartz grains that have survived countless cycles of weathering and transport to the delicate clay crystals that form and dissolve on timescales of centuries, are not merely inert particles filling space between roots and worms, but active participants in a web of interactions that sustains life at the surface of the earth. And the slow, unhurried process of coming to understand these interactions, one careful measurement and one painstaking observation at a time, continues to occupy the attention of soil scientists around the world, who find in this most earthbound of pursuits a source of intellectual engagement that, however unlikely it may seem to the uninitiated, is genuinely inexhaustible in its capacity to reveal new details, new patterns, and new questions about the ground beneath our feet.